So with that, I don't want to take too much of your time, Joachim. So please, thank you for being with us, and please, the word is yours.
Thank you, Jean-Charles. Your announcements give me the opportunity to thank you for putting together with your team a digital conference in difficult times. Thank you very much. And I like to thank the organizers for giving me the opportunity to speak. And Ampero, thank you very much for your kind introduction. As a technical note, when I tried to practice with this digital form of a presentation, we realized that sometimes you have to press a refresh button on the right-hand upper corner of the presentations of the screen, and that's when you observe a gray shaded screen. And with that, I'd like to start with my presentation. I'm going to speak about a new approach for constructing analytic equations of state. And in my talk, I'll introduce a theory. I'll introduce some technical difficulties. Here we go. I'll introduce a theory which is chains. So first, I'll speak about a new theory that I refer to as UF theory. My co-author is Thijs van Westen, and I'll then modify this theory to a second version, if you will, which we refer to as UV theory. I'll turn to chain molecules in a Saft formalism and just very briefly speak about inhomogeneous systems with a DFT formalism. And then what I'd like to convey is that this is, I find, a suitable framework for building equations of state for our community. So the motivation is clear. Most
Joachim, sorry to interrupt you.
Yes? Yes, Ampero.
I don't hear you, but I think if the audience are hearing you, I will.
Okay, maybe we can have a second.
Try to sort it out, or I will find someone else to chair. Can everyone hear Joachim?
Yeah, we can hear clearly. Loud and clear.
Okay, so I think mostly people can. Okay.
Okay.
So to interrupt you, carry on.
Yes, thank you very much.
Sound. I will ask someone else to chair for the questions. Sorry about. Yeah, go on.
And thank you very much for the feedback in the chat that I'm heard. The motivation is clear. In engineering, we usually rely on perturbation theories, and these perturbation theories, they converge rather slow. So this is a first order theory in the description of a Lennard-Jones with red line, a second and third order theory. And you can see it converges rather slowly. And a third order theory is really rather involved for mixtures. So I think we need alternatives. And with that, I would like to turn to perturbation theory, and I'll introduce the subject. This is a bit heavy for an keynote lecture. I'll be slow and present a few slides on the theory. So Perturbation theory is really an approach to describe a target fluid, and we can think of a Lennard-Jonesian with an intermolecular potential U. So this is a Lennard-Jones representation, and we'd like to describe this fluid based on a reference fluid, which I refer to as U0. And U0 can be anything. I here represent a hard sphere fluid, but really it can be anything. And when I say anything, it has to be a fluid with known Helmholtz energy and known other quantities like a radial distribution function. There's a disclaimer to what I said. I said it can be anything, but the target fluid needs to be contained in phase space of the reference fluid. And this is a bit of a subtle point. Sometimes in hard sphere fluids, for example, part of the phase space is really cut out of by a hard sphere fluid. So this is a bit of a subtle disclaimer. So what we do is we define an intermolecular potential U depending on a coupling parameter lambda. And lambda ranges between 0 and 1. And lambda makes a transition from 0, where this potential describes a reference fluid, to 1, where we describe the target fluid. So it's clear what we do. We integrate the Helmholtz energy from the naught, so from 0 in lambda to 1 in lambda. So that's how we obtain our target fluid. And now I had here just a second ago, try to redo it, a linear scaling of the coupling parameter. It doesn't have to be linear. So we write this more generally like so. And linear is just one way of doing it, a linear coupling parameter on the perturbing potential. And this perturbation is suitable for shallow parts, attractive parts of the intermolecular potential. But we can also use another way of acting for the coupling parameter to act on the perturbing potential W, and that's a logarithmic form, and that leads to the so-called F expansion, which is suitable for steep parts of the pair potential. So if we now want to describe a Lennard-Jones fluid or a Mie fluid, and here's the mathematical form of the Mie fluid with a repulsive exponent, which is 12 for Lennard-Jonesian fluids and different for other Mie fluids. If we want to describe such a fluid with this potential, then we usually proceed in 2 steps. First, we start with a hard sphere fluid, green, and make a transition to blue, a soft repulsive fluid. So this is a first perturbation theory. And then we do a second perturbation theory where we add the red attractive part of the potential. And it doesn't matter conceptually how we divide this potential. There are 2 famous ways of dividing the potential. The upper picture is for the Barker-Henderson and the lower for the Weeks-Chandler-Anderson choice, but there are infinitely many choices, and I will consider both choices in my talk. So let's start with the upper right perturbation theory, the first perturbation theory in making a transition from the hard sphere fluid to a soft repulsive fluid in blue. And I said the F expansion is suitable for steep parts of the potential. So here we go. I do not show the derivation of this equation, but it's really simple. It's a derivation in 2 or 3 lines, really. And what I'd like to convey is, well, we have an expression for the Helmholtz energy A0, blue, based on a hard sphere fluid with a first order term here. And that first order term contains the potentials, hard sphere fluid potential and the soft repulsive potentials. And it contains a radial distribution function somehow modified. It's called cavity correlation function. So in the original Barker-Henderson theory, this whole term was omitted. If the diameter of a hard sphere fluid is chosen appropriately as a function of temperature, this whole term can be omitted. Weeks, Chandler, and Anderson, they worked differently. They sort of nullified this term, set it to 0, and thereby determined a suitable diameter of a hard sphere fluid, which is now a function of temperature and density. So T and rho. Now, we don't do that. We take this term along. We let the diameter only be a temperature-dependent function, not a density-dependent function, for two reasons. First, we'd like to avoid the iteration of a diameter which is density-dependent. And secondly, the Weeks-Chandler and Anderson description leads to diameters that are at low temperature and high density so large that the hard sphere fluid actually makes the transition to a solid phase. So we'd like to avoid that. Now, we take this term along, and this is the blue fluid, the soft repulsive fluid. Let's now proceed and add the attractive part of the potential. And commonly, this is done with a U expansion. So we have a repulsive, soft repulsive blue fluid, and we add the red part of the potential. And this is done in the formalism that I just showed. We simply have this equation that we put the partition function into, and we obtain in 2 lines this equation. And here comes the actual expansion where the radial distribution function is expanded around the reference. So this leads to a first order theory the way I write it, but higher order terms are here, appear, and they are not written out. I'd like to note the terminology here. This is the first order U expansion. I'd like you to memorize this, this part. And what is known is that the first order theory is an upper bound. The Helmholtz energy can never be higher than the first order U. I'll move this equation upward in the next slide. So here it is. We could have also chosen to do an F expansion. It's not an obvious choice because it really converges rather slowly, but it has one nice feature, and that is it is exact in the low density limit. This first order theory is exact in the low density limit. And in the following slide, I'll show that this is effectively the first order theory, a lower bound. And I'll use the terminology delta A1F for the first order F expansion. I'd like you to memorize that. So here we go. I have to show this is a lower bound. What we see is a Lennard-Jonesian fluid and 3 temperatures. Red is molecular simulation data, Monte Carlo data. Green is the first order U expansion, which is an upper bound, and blue is the first order F expansion, which is seen to be indeed sort of a lower bound for the temperatures we consider here. And that's an important finding because now we know the Helmholtz energy is bound to both directions by a first order U expansion and a first order F expansion. So the real Helmholtz energy has to lie between the two. And that leads to the approach we're taking. The Helmholtz energy has to be in between a first order U expansion and a first order F expansion, and we introduce, you could call it an interpolation parameter, phi U, the U fraction. I'd like you to memorize this term, and I'll speak about a U fraction in the forthcoming slides. And the Helmholtz energy has to be between the two, so phi has to be between 0 and 1. This equation is a first order theory, very simple for mixtures. So both terms are exactly known for mixtures, can be written out, explicitly and simply. But of course, phi is itself an equation of state. Let's look at phi. Phi needs to start from 0 because the F expansion is exact in the low density limit, and it has to approach unity from below at high densities, because we know the U expansion is a rather good description of the fluid at high densities. So the U fraction cannot go anywhere. It has to make it sort of a nice transition from 0 to high values approaching unity. And what we observe, it's not a strong function of temperature. That's fortunate. we see 3 temperatures here for a Lennard-Jones fluid, 3, 2, and 1.4 in temperature. With symbols, I realize now it's difficult to see in the slide. We see data from coexistence of vapor-liquid coexistence data. And we see it's not a strong function of temperature. It's a very smooth sort of transition. And we can easily fit a function, and we used a simple ansatz function in dotted line here. Now, maybe you realize that the green line, and even the blue does so, goes above 1, which it may not do. And but that's not, sort of caused by the UF terms. It's caused by inaccuracies in U0. And here I show again the equation I showed, and we had to omit sort of higher order terms, and this causes this artifact. But it's very insensitive, and I'd like to trivialize this so it doesn't hurt us much. So with this dotted line, which we adjusted, it's a very simple tangent hyperbolicus function with 2 parameters independent of temperature. We get a description with a dark black line. And this is a vapor pressure line for Lennard-Jones fluid, and this is coexistence density data. And we observe a marvelous description with, average errors way below 1% in vapor pressure and in coexistence densities. Look at other quantities. These are isotherms, pressure versus density, internal energy versus density, and heat capacities. And we observe a real good description of these thermodynamic quantities. And mind, it's a first order theory. We sort of also get a good description of this difficult behavior, the heat capacity at constant volume. Authors have in the literature stated an analytic equation of state cannot describe this well. And the reference in pinkish color is a third order theory, third order. So this is an expensive sort of theory. Now we were happy about this, but not all the way happy, because the F expansion is difficult to extend to chain molecules, to non-spherical molecules. So we continued, and Thijs van Westen did so. So let's look at the F term here. The F term in the low density limit is exact, I said. It's sort of a virial expansion. And what Thijs proposed, Thijs van Westen, and here you see an image of Thijs, my co-author. What Thijs proposed is to use a virial expansion, but also using the first order U expansion. So this is going to be a tighter bound. If we replace this term by that term, we get a new equation, and we refer to it as UV theory, and V is for virial expansion. And this is an even nicer equation, if you will, because the virial coefficient is known. There's no ambiguity about mixing rules. And here we see on this slide results. And in turquoise color, we see it is, yes, this V bound is indeed a lower bound. Effectively, oh, who is manipulating my slides? Okay. This is indeed a lower bound, and it's a tighter lower bound, so that's very convenient. All the nice features that we observed will also be true for this approach. Here we see again various temperatures for a Lennard-Jones fluid. We obtained these lines by using an analytic equation, which is very accurate, the equation of Monika Toll and co-workers as a reference, and you observe the same fine behavior that we just have seen. So we can again adjust a simple ansatz function, and we used a tangent hyperbolicus 2 parameters and get rather, very good description. So here we go. Maybe you concentrate on the green line. This is the result for the Weeks-Chandler-Anderson division of the potential, and the green line is in vapor pressure, in a pressure density projection, and the coexistence behavior of a Lennard-Jonesian fluid. We obtained a very good description of the critical region. It is a classical theory, so it's not showing universal scaling behavior, but it really gives an improvement even compared to third order perturbation theory, which is in this reddish or pinkish color. So we see this improvement also in deviations. These are deviations in various quantities, in density liquid, density vapor, vapor pressure, and enthalpy of vaporization. And the theory really outperforms a third order perturbation theory. So that's encouraging. The heat capacities, green color is the one that I am just discussing. And the old theory, so to say, is back. We have a bit of a better performance of the UF expansion here, but a wonderful description altogether. So let's turn to Mir fluids. Mir fluids are described with one additional parameter. This is the parameter. And with this parameter, it's possible to describe the family of Mir fluids with surprising, to my mind, surprising accuracy. And that's true for vapor pressures and densities, and also at conditions above the critical condition. With that, I'd like to turn to chain fluids with the SAFT statistical associating fluid theory formalism. And the equation we're using is this equation. So we have a description for spherical segments, you could say, in the language of SAFT. So this is a description I have just discussed. Let's now speak about the chain term and the attractive parts of the potential. And I'll start with the chain term. The chain term is based on Wertheim's perturbation theory of first order and the SAFT formalism developed by Walter Chapman and George Jackson and Keith Gubbins. So this is the first order term here. Now we observe, of course, for low densities that the first order theory, and this is well known for longer chains, and this is the number of segments of a chain, starts to deviate, and especially so for low density. So we add a second term here, and we in a way use the same formalism that we have applied before. You could add several things. You could add a second order Wertheim theory here, but that would improve things a little bit. You could add description according to Liu and Hu, which improves things a lot. So we have for a long time worked with that expression, but we have turned to this sort of approach where we again use the virial, second virial coefficient of chains and sort of correct it in a second order term, because this is also nice for mixtures. So this is well behaved. Now we obtain blue and we manipulate it empirically with a red term to get a real nice description for chain fluids. So this is sort of an empirical but well behaved extension. What I'd like to convey is that we're concerned about every term of this equation of state to really have an accurate description. What I showed before was tangent hard spheres, and this is now chains of Barker-Henderson repulsive fluids, and this is also giving a good result. Anyways, so the second virial coefficient is needed in this equation, and Thijs van Westen has developed a model for that. This model is representing the data rather accurately, and it does also approach the polymeric scaling behavior for large chains. So that's a difference compared to the Liu and Hu equation or the TPT1 or TPT2 equations. So with that, we can look at chain fluids of Mir chains. This is a Lennard-Jones chain result, a dimer, 5-mer and 8-mer, and the result really confirms in all quantities. We looked at a very satisfying description, let's say. So what does the UV theory give us? This UV framework allows us to construct equations of state for a species. And the task of developing an equation of state for a species corresponds to developing a description for this U fraction. The rest is simple. It only requires first order terms that are very simple for mixtures and unambiguous. This function, the U fraction, is well behaved. Simple ansatz functions work. We have the ambition of providing a description for this ansatz function for chain fluids in the SAFT ecosystem, so to say. The U fraction is hardly temperature dependent, so we propose just a density dependence. Mind. By refining the U fraction, one can obtain an arbitrary accuracy in the description of a fluid. So think, if you will, you wanted to describe propane very accurately. There's lots of experimental data in a description similar to what Roland Spahn does in highly accurate equations of state. Now, you can sort of adjust SAFT kind of parameters, have a molecular model for a Mie type of chain, and then refine this U fraction to obtain an arbitrary accuracy in the description of your experimental data. And what I'm convinced of is that this so developed equation for propane is compatible with the entire SAFT ecosystem for these fluids. So I think that's a strong point, and it is also suitable for inhomogeneous systems. So that's why I think this is an interesting subject for our community. Should be interested in mixtures, but really, I'm not speaking about mixtures because Thijs is giving a presentation this afternoon. Just as a teaser, maybe Thijs finally solves a long-standing problem of for example, Lennard-Jonesian fluids of different size, and this sort of phase behavior could never be described with a one fluid theory approach. Unless there's fortunate cancellation of errors, and he sort of solves this problem and presents that this afternoon. Just a brief glimpse on inhomogeneous systems. What is needed for inhomogeneous systems is a Helmholtz energy as a functional of density, and well, we have practiced to develop such functionals for the PC SAFT equation of state, and there are two talks on this conference by Johannes Eller, one talk, and by Philipp Rehner, another talk, where these functional Helmholtz energy functionals for PC SAFT are used to look at surfactant systems or microporous systems. So yes, we do have some experience in this, and we can apply this the same formalisms, namely weighted density formalism, also to this UV theory. And here we look at surface tensions of various Mie fluids with repulsive exponents 12 for a Lennard-Jonesian fluid, and different exponents considered in this diagram as well. This result, this is sort of a liquid film, a very sensitive result, in actual, or a sensitive system, a very thorough test for an equation of state. Rather, I'd look at radial distribution functions for various Mie fluids in orange color. This is a Lennard-Jonesian fluid, and the way this was calculated is that a Lennard-Jonesian fluid acts as an external potential onto a Lennard-Jonesian fluid, and the resulting density profile corresponds to the radial distribution function, which can be sampled by molecular simulations in these symbols. And this is a, sort of a consistency check with good results in this case. I'd like to show a conclusion slide, but I'd like to mention I have two more slides after the conclusion. So here's my conclusion slide. The UV theory is giving us surprisingly accurate results for spherical Mie fluids and also for Mie chain fluids, we have started to look into inhomogeneous systems and found promising results. There's a picture of Thijs van Westen, who is really driving the work. And I also have a picture of myself, if you're interested. There it is. I like to spend my time in the green if I have time, and maybe a bit of a coarse-grained representation of reality. They're open issues. What I'd like to work on with, and Thijs would like to work on, is chains that are not fully flexible. A fully flexible chain is not a reasonable and good representation of real molecules. So, and our theory is really simple to account for intermolecular bond potentials. Secondly, group contribution approach is open. I think that's needed for a theoretical framework to be successful. And what I'm proposing to the ESAT community, to us, is I think this may be a suitable framework for constructing equation of state models. The reason is that models can be constructed very accurately if you refine this U fraction, and this can lead, in my mind, to a full ecosystem of a thermodynamic model that is suitable for mixtures and for inhomogeneous systems. And I think the time is over where a single group sort of develops or proposes a model, and then this model is either used by others or modified. And I think we should jointly work on this problem. In order to facilitate that, we are about to publish a software framework for equations of state. It's an open source framework developed by Gernot Bauer and Philipp Rehner. What is needed for you to do is you implement an Helmholtz energy, and only an Helmholtz energy expression or an Helmholtz energy functional, which you can implement either in the coding language, programming language Rust, leads to a fast code, or in Python, which leads to a fast development. It's a convenient sort of environment. Derivatives are obtained exactly using hyperdual numbers, so they don't need to be implemented by you. Of course, this is a sort of a modern software environment with standard file formats. Some equations of state are implemented, pieces halved, and the UV theory, an SI unit system is in place. There are many features. You can compute properties and for pure substances and mixtures, but also phase equilibrium calculations, flash calculations, diagrams, just pure substance parameters, calculate critical points, just KIJ parameters, and so forth. So it's a powerful framework. Back one slide. Because this is important, we have for many years worked on density functional theory and developed code that is suitable in 1 dimension, in 2 dimensions, cylindrical coordinates, Cartesian coordinates, 3 dimensions. And this is all implemented in this environment and can be used. So Rust is a fast and fail-safe language, a modern language. Python doesn't need advertisement. This is, widely used. An example for how to calculate phase diagrams is shown here. You load parameters by this statement for a mixture of acetone and hexane. You load or build the equation of state by this command, and then you can go ahead and compute things like phase diagrams, pressure X, or isobaric, so TX diagrams, for example, like this. And the 2 developers are Gernot Bauer and Philipp Rehner, and this will be released, this code, in October. So with that, I'd like to show my conclusion slide again. I think, this is meant to serve for us as a community in constructing equation of state models, building an consistent ecosystem, and thank the organizers for giving me the opportunity to speak, and I invite questions. Thank you very much.
Thank you, Joachim, for a very nice talk.